We're going to be finding length, distance. We have a formula for that. We have two different formulas for distance and stuff, and I'll show you why there's two different ones. We're going to talk about midpoint. That's a vocab word. Talk about the formula to find it. And then the last word we'll get to, hopefully we can get to today, is the word bisector. All right, but let's jump right in. Let's talk about length or distance. We'll do the definition here. Okay, so length. The length of an object. It's usually, we talk about the length of a segment. It is the actual distance between 2 points. Between 2 endpoints. The actual raw distance. There's a numerical value to it. So we're seeking out a value, a number, a digit, something we can do. Now, you can find length on two different types of pictures. You can find length or distance on a number line. So that's going to be one of our examples we're going to do. So the two types we're going to be looking at today. We're going to find it for a number line. And the second thing we're going to find it for is the Cartesian coordinate plane. Cartesian coordinate plane.
So that's C or an A?
On the front?
Yeah.
Yeah, that's a C. So Cartesian coordinate plane. So there's two different formulas we have to cover. So I said we're going to have two formulas to find distance. The number line is probably one of the easiest, but it's the one that some people like. They don't understand why it works, so I'll discuss. We're going to do two types today. All right. Questions about what we're doing here? Give me a little bit of time to write notes and pushed over there.
You gonna come in? What do you need, 100 figures?
Okay, we're gonna question.
What is a Cartesian coordinate?
We'll get to it. I'll show you a picture. It's a big fancy word for something you've already seen before, but we'll discuss. It's a great question. We'll get to that. Not a boy. All right, let's jump right in. Let's do the number line first, and we'll get to your question. What is a Cartesian coordinate plane? So number line first. Number line, pretty traditional. There is a property that we'll eventually get that will explain the actual number line itself. We'll wait for right now. Here's the number line that you are traditionally used to. Okay. Number line has 0 in the middle. That's usually what we always have. There's an actual term for that. That is called the origin. It is the center of the picture. There's an origin for the Cartesian coordinate plane as well. But once we get to that. Now, as you go to the right, what numbers do you hit?
Positive.
Positive. That's usually what you always hit. 1, 2, 3, 4, 5, 6. Okay. Now, when we get to that property later about number lines, they just explain that really the positive numbers don't have to be on the right. They can be anywhere. This is an imaginary object we created in math. You could draw it any which way you want, up, down, right, left. It really doesn't matter. But for the purpose of keeping it very similar to what you learned in like elementary days and junior high days, yeah, we keep it like that. It's just to be safe. Okay? And then as you go to the left, obviously, we're hitting negatives. All right, so -1, -2, -3, -4, -5. Now, as you're going to the left, the numbers are getting smaller. I know that's really a weird concept to say, because I'm going to be writing -6, -7. Those numbers are getting smaller, if you can think about it. I know that's a very awkward thing to describe to somebody. Now, what we're going to do is find distance. I'm going to pick any 2 points up here, and we're going to find the raw distance between them. It doesn't matter which two numbers I pick. So I could pick -3, and I could pick 2 for all I care. We can find the raw distance between them. Number one, you can count with your fingers. It's common sense how many like little sticks are between there. So you could just do this. You could just count the gaps between markers. So if I count those, what is that, 5? There's 5 gaps between 5 sticks. That's fine. You could count with bunny leaps. Maybe you're that person. 1, 2, 3, 4, 5. That type of thing. I don't know how you do it. There's always that one person in the room that will get it wrong because they always start with the first number and they count that first. So to save you from making the horrible mistake of not knowing how to count with your fingers or count the sticks, there is a formula to find the numbers. So the numbers we're going from is -3 to 2. So maybe they put variables on the picture. So maybe they actually have this picture labeled. So they have a picture labeled and they have this, let's call this A to B. And they want you to find the actual raw distance from A to B, and this is how they mark it. They want the actual distance. They left the bar off of it, so that's a segment, and they want the distance, the actual numbers. So that would be the 5 that I just told you a little bit ago. But there's an actual formula to find it, so you don't have to think about it or you don't have to draw it. Here's the formula, whatever the two numbers are. I'm going to use the A and B as my little thing. You can pick A or B first, it really doesn't matter. You're going to subtract whatever the two numbers are in any order you want. But when you do that, you're going to put absolute value bars around it. That was one of the vocab words I think we've discussed already. And it doesn't matter the order. So if you're that person that wants to go B first and A second, because again, it doesn't really matter the order you write it, as long as you put absolute value bars, you're going to get the same answer anyway. The distance. I know that seems kind of weird. It will work every single time. Because absolute value bars, whatever this answer is on the inside, the absolute value bar is just guaranteed that it's positive. That's all an absolute value bar does. Just make it the positive number. So A to B. Let's put it in that order. Let's do A first. A is -3. So you're going to write -3 first. I'm going to subtract whatever it is. I'm going to subtract. I don't even care if the next number is negative. I'm going to subtract whatever that next number is. Now what's my B number? Put a 2. So what's -3 minus 2 more? -5, right? And the absolute value bar, make sure that it's positive. That's it. So the answer is 5. Well, we already said that, right? You counted with your fingers earlier, you did the picture, you counted, it's 5. Perfect. It works the same on the bottom. This bottom equation will give you the same answer. So I had B written first. Well, the B number was the number 2. That was B. I'm going to subtract A. A is -3. So I'm subtracting the negative. Well, what happens to two negative signs? They cancel out, right? Two negatives that are touching side by side make a positive. So that's 2 plus 3, which is 5. And the absolute value of 5 is still 5. So it doesn't matter how you do it, the formula works every time. This is the formula I'd like you to have written down. It doesn't matter the order you subtract, as long as you put absolute value bars, it will work every single time. All right, questions? Questions about the number line and how to find distance on it. Okay, how do you know that? I could have any number sitting there. It didn't have to be whole numbers. Your book will eventually give you decimals. Yes, you have to be able to subtract decimals or fractions. That's something we're going to probably practice more tomorrow. Just to make sure that everyone's kind of on that same page. Okay, we're good with the whole number line. We'll practice that more tomorrow. Because I said I want to do decimals, I want to do fractions. I want to have you try some out by yourself, have you try in different groups and try different numbers. So just be kind of aware of that. Okay, let's go to the question of the questions. What is the Cartesian coordinate system? Let's discuss. That was the questions we asked earlier. Cartesian coordinate plane, here it is. This is the Cartesian coordinate system. It's the coordinate plane. It's an XY graph. You probably saw it a lot in Algebra 1, correct? Okay, good. It's the main thing we use. It is a 16th century, that's like the 1500s, 16th century math concept made by a French mathematician, René Descartes. 16th century, 15 something, it was created. We still use it. It's used in everything we have now. It's used in maps, it's used in GPS, it's used in your phone and your computers, for the love of God. That's how the matrix screen on your computer and your phone actually work. That they're actually projecting pictures or colors to a certain pixel on the screen, because the pixels represent the actual blocks on there. If you actually look at a computer screen or phone screen really closely, I guess anymore it'd be almost impossible to see it, since the pixels are getting so small. But back in the day, you could actually see the individual pixels. In fact, if you come up to my marker board, you don't have to, you can actually see the individual blocks, the pixels that are up on that board, because you can actually see the grid that's behind it. You can actually see it now. From you, it's just solid white, but there is an actual grid here that I can actually see. And it's using this concept, a 15th century math concept. We still use it in technology today. But all it is, this grid, just don't think of I know it gets confusing for people, but the grid isn't there. Okay, it's a fictitious object. All these little hash marks aren't there. The things I want you to focus on are the really dark lines. In fact, I'm going to highlight those just so you can see them. I'm looking at these two lines right here. If you really concentrate, you can see them. Sometimes they blend into the others, depends on how good your projector is or screen. Those two lines. All I want you to think of is those two lines, they're labeled with X and Y. They're two number lines. That's all it is. You have a number line going, on the X. You have a number line going up and down. That's all it is. Just two number lines put on top of each other to make a crosshair, to make a T. And now that you can see that they're just two number lines, we use both of them to find spots on this grid. That's all it is. So when we say it, so the Cartesian coordinate plane is two axes. So there's an x-axis. That's one of the number lines. That's the horizontal. And then there's a y-axis. That's the vertical going up and down. Now, there's still an origin to this. The origin is still the center of the graph. It's still the main crosshair in the middle. Because it's the center. It's the center of both number lines. That's zeros. But to get anywhere in this graph, we use what they call an ordered pair. Okay, it's called an ordered pair. Now, most people don't call it that anymore. Most of the time when you hear that term ordered pair, it's a big fancy word for a coordinate. That's probably what you've heard, probably in Algebra 1 a lot. Find the coordinate for this spot. What are the numbers that are involved in that spot? Okay, so how do we write coordinates down? Does somebody have an idea how we do it? Wheeler, what do you got? How do you write a coordinate? Give me an example of a coordinate.
2, 4.
2, 4. Okay, perfect. That's an ordered pair. We use parentheses, we separate numbers by commas. They can be positive, negative, they can be decimals, they can be fractions. It doesn't matter. Anything you want, as long as you have the actual pair of numbers. Now, why it's a coordinate, why they call it an ordered pair? They're in alphabetical order. It is a pair of numbers, two numbers, you can see them. We look at two numbers. But they're in order. They're alphabetical order. So what's the first letter of the alphabet in those two? X, that's why it's X first. They're literally written in alphabetical order. X first, Y second. X, Y, Z, right? So it's alphabetical. So when you're doing this, you give me the horizontal number first, then you give me the vertical number second. So the X number is the 2. So if you think of this as my origin, that's 0. This is the X-axis. This is just a number line going this way. And number line going back. So it's just a big fancy number line. So the first number, you find 2 on the X-axis. So boom, it's right here. So I'm right on that marker. And then I have to find the second number, which is the Y. That's the number line going up and down. So that number line is, so if you turn your head, this is number 1, this is number 2, this is number 3, that's that. And we keep going. We have -1, -2. It's just a number line going up and down. So if I'm going to 2, 4, I find 2 on the X, find 4 on the Y, and that's where the dot goes. And I can call that point A for all I care. It's a location in space. Label is a capital letter. Now, the best way I describe it to the people, some people do get mixed up. Some people do get mixed up. Thank you. With which way do they go first? What numbers do you find? How I always think of this is, imagine this is a hotel, a really big hotel. This is the lobby. You walked into the lobby. You have to pick an elevator first. Once you have your elevator, then you can go up and down it. So you have to pick your elevator. That's the lobby. So you have a basement. You have an upstairs. You find your elevator. I'm in the second elevator. I'm going to the 4th floor. 2, 4. It could be any number. It could be decimals for all I care. And you can still get there. Because technically the grid isn't there. The grid is just extending the number line hash marks, extending these so they're longer, and then you can see where they all cross. That's all they're doing on that picture. So the grid technically isn't there. But that's a coordinate plane. Now why they use it for GPS on your phone? Because your phone, like if you're looking at like an iPhone or an Android phone or whatever, maybe you're on your Chromebook for all I care, the screen is here. There's your screen. So this is the bottom corner, on a Chromebook. This is the menu on the bottom, so you have your icons. And then you have, your browsers open. But this is the screen. You can really start to see it if you use like Photoshop on a Mac, or if you use any type of apps that are like paint-based programs on a computer or a tablet or anything. Because when you're coloring or you're painting, you're doing something on that thing, there's usually coordinates written down in the corner. They usually have them somewhere. And you can see, like when you move your cursor, you move your mouse, you move your finger, the numbers in the corner start changing. Because they're telling you what pixel you're on. You're at a certain coordinate. You're 2 over 4 up. Or you're at, 1,000 over 900 up. Because your computer screen actually has a certain number of pixels. So when they say on your Chromebook, it's, they say it's something like, it's like 980, or it's 1080 by 980 or something like that. That means you have so many pixels going across and so many pixels going up. So this is your 1,800. You have 980 pixels going up, and this is your pixels on your screen. So each one is a pixel. There's 1,000 going across. So the more colors that your screen can show, the more vibrant, the more pixels, the more options it can have, and it can have better density. So I think one of the things they always talk about is like the iPhone and those Samsung Galaxy phones. They have the best color gamut because there's so many colors they can light up per pixel. I think the new iPhones and most Samsungs are now OLED screens now. The new iPhone X's. That means you can turn the pixels off, so they're completely black. That's different than just a normal phone that has an LCD. You can't turn the pixels off; they're always glowing. They're backlit. So there's difference, but you're seeing it. That's a kind of a nerdy way to think of it. That it's in the corner, but it is. It's just a dot matrix screen, and it just prints by knowing what pixel to light and where your cursor sits and what you click on, and it knows the pixel behind it and what app that is. It's not really a clever system. Just to give you an idea, I have one of the original Macintoshes that came out in like 1980. Right? That's one of my first computers I ever bought. Yeah, I'm that old. But you couldn't have multiple windows up on your screen. It was like kind of one window at a time, and you could close it down. Then you can open up another window. A Chromebook's very similar. I think nowadays you can put 2 windows on the screen now at once. The original Chromebook you couldn't. You could only have one screen at a time. Now you can have overlapping windows, and you can click through, and you can click the back window to come forward, and you can do all these fancy things. The original iPhone, you can only have one window screen at a time, one app open. Now I think they can do split screens and stuff now with the newer thing. So because they can have depth to the screen now. So there's this is the concept. It's a simple mathematical concept, but we use it in almost everything. It's just, but to me, seeing that first day of it, you got to see the importance of it. You still use it. So if you're going to go into computers, or you're going to go into art, you're going to be into technology, you need to know the concept of math behind it. Because some artists are so particular that they're going down by pixel. They want to light a certain pixel by a certain color. There's an art program that you could do on a matrix printer, on a printer, just a color printer, where you could take, I think it was called like, raspberry paste or something like that, where it was you could take a photo, like a really big photo, and you could break down the photo into certain pixels, like certain grids, so like a 9-grid system, and you could print the picture out on individual pages of printer. And then you could put them all together and it makes a huge poster on your wall. But it's doing this, it's taking your photo, putting it down, and then it's just printing individual pages that would represent your picture. And you can just put them all together and make your little puzzle out of it. That's exactly how a puzzle works when you buy one of those actual like hand puzzles that you're gonna put together. Now, to talk about what we're doing with this, we're finding distance. This is one of the most challenging things to do, is to find distance on this system. If the numbers are straight across, yeah, it's pretty easy. Numbers are like that, it's pretty easy to find the distance between the sticks because it's horizontal, right? That's what, 3 bunny leaps? You know, there's actually 3 sticks. But we're not going to do that. What we're going to do is we're going to actually find distance if we went diagonal, not just straight across or straight up and down. Because straight across and straight up and down are very, very easy. We're going to find it when you go diagonal like this. Because if you go diagonal, that stick is not perfectly 4 pieces long anymore. You know, there could be individual decimals that are involved here. What you're seeing here is the first instance where you have what they call irrational numbers, the potential for irrational. Well, we need to discuss this. That's one of our concepts today, is to talk about what an irrational number is. So my first example is to show you what we're going to be doing. Like we'll do an example here, I'll have you write it down, and then I'm going to show you the concept behind it. All right, so here's your formula. I'd like to write this formula down. So distance equals, so here's your formula. A big square root, the big radical sign. I'll explain that concept here in a minute. We're throwing in the deep end here. Big square root symbol. On the inside, you're going to subtract 2 x's and put a power 2 on that parenthesis. So whatever 2 x's are, subtract them, put a power 2 on it. Then you're going to add. You're going to subtract 2 y numbers and put a power 2 on that. That is your distance formula on a coordinate plane. Now, it looks, do you agree that looks way more complicated than what we did earlier? Like way more complicated. In fact, it is. It's way more intensive. So in fact, I'm going to use the coordinates we used earlier. So one that Wheeler said earlier was 2, 4. Here's point A. 2, 4. In fact, I'm writing these down. Point A was 2, 4. I need a different coordinate for B. Any numbers can be positive, negative, I don't really care.
3, -7.
3, -7. 3, -7. Boom. Let's draw that one. So 3 over, -7 down. 1, 2, 3, 4, 5, 6, 7. Here's B. That is a very steep diagonal line. It's not straight up and down. It is very steep. That is incredibly long. If you want to guesstimate, I use that word guesstimate, but if you want to guess on how long that number is, approximate. You know, if you kind of hold your fingers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, about 11-ish or more, could be less. You know, if I'm approximating how long it is, you know, if I just use my fingers as how many bricks it would be, it's about 11 in length, 11 bricks in long. I just hold my hands up. But to actually find the distance, you use these x coordinates and you use these y coordinates and you plug in these numbers into that formula right there and it'll give you your answer. And this is where you need a calculator to type these in so you can give me the actual number. I'll show you tricks on how to do that without a calculator. Okay, but let's just write this down so you have this first. So we're going to plug these numbers in. I don't care what order you put these x's. It makes no difference to me. because you're going to square it anyway. So that's kind of nice. It's kind of like when you put the housing value bars. But we're going to subtract the two numbers. Okay, so tell me any of the two x numbers in any order you want. 2 or 3, which one do you want first? 3, okay, so we're going to go 3 minus 2. You subtract the two numbers in each square, right? You subtract the x's. Okay, the y numbers, any two in any order you want.
4.
4 negative 7, so 4 minus the negative 7. Yes, you're always subtracting. You're even subtracting the negative 7. And again, you could put them in any order you wanted. You could put negative 7 minus 4 for all up here. Okay, questions with how we set that up? Okay, now, the goal is to type in your calculator and figure this out. So this is where, if you have one of my calculators, or if you need to go borrow one, I have them in the back, so you can get some practice. If you have your own, take out a calculator right now so you can get some use to this. Because that way I can show you how to do it on yours. And remember, whatever calculator you learn it on, that might be the calculator you want to use on the test. They're in the back. They're underneath the, yeah, they're underneath the pencil sharpener. Sorry. Yeah, just put them on the desk back there. Yeah, remember, if you borrow one from me, just make sure I get it back before you leave today. I'll give you a little bit of time here to go get a calculator and whatnot. Excuse me. Okay, everyone's got a calculator out, ready to go. Everybody that has a scientific calculator should have a square root key on it. Now the goal is to figure out where it's at and how to use it, because that's like the number one thing people always struggle with. It's like, I don't even know how to type that in. I'll show you here in a minute. Okay, let's do most of this by hand until we need to type it in, because if you try to type everything in at once, you'll screw stuff up. So let's do it by hand until we get to the final answer. So what's 3 minus 2? 1, so we're going to square that. Okay, I'll explain that here now. Okay, and again, if you want to put parentheses around it, that's probably a safe bet. You can do that. Now, 4 minus a negative 7, well, that's what? 4 plus 7?
11.
So that's 11, so it's 11 squared. And again, you can put a parenthesis around it, especially if it turned out to be negative, you'd always put a parenthesis around it. Now we're going to square it. What that means, you're going to take that number times itself. When you do that, these numbers should always turn out to be positive when you square it, because you're taking a number times itself. So if it's negative, negative times a negative is still positive. They cancel out. So 1 times 1 is 1 plus 11 squared.
121.
Yeah, so this is 1 plus 121. Is 11 times 11 is 121. So we're going to add them together, so we have the square root of 122. Okay, make sense? Like how we did this. Squaring a number times itself, that's what a power 2 means. Now, what this is a radical. What you're doing, what a radical is, a square root, is you're trying to think of a number that multiplies on itself that gives you 122. It's not a nice clean number. Here's the reason why. Okay, because we're trying to break down the square root of 122. Jeez, let me get rid of that. Get rid of this graph right now. All right. So to break down 122, you're trying to think of a number that multiplies on itself that would give you this number on the inside. The number on the inside, by the way, is called a radicand. We'll write this stuff down tomorrow. Today is just to show you the introduction. It's not clean. It's not a nice number. The reason why I know it's not a nice number, because 121 is the clean number that's really close to it. 121, if we were to take the square root of that, that's 11. 11 times 11 is 121. So the answer for the square root of 121 would be 11. 144 would be 12. Well, do you agree that this number right here is in between 144 and 121?
Yes.
So it's the decimal between here.
11.04.
Yeah, 11.04, right? Because how I know that? It's insanely, 122 is insanely close to 121. So the decimal has to be close to 11. So 11.04?
04.
So the decimal is trying to be 11.04. Couple decimal places in. That's the approximate answer. So now, how do you type this in a calculator? On most calculators, you have to hit the square root key first. So on my little calculator up here, the square root key is right above this little x squared key. So to do this, you have to hit the little second key, I call it the shift key. second, and you hit the little x squared, so it puts a little squared symbol on there. Don't use the one above it that has a little x on it. I want to use just the square root key. So you hit second, hit the square root key, and then type in 122, hit enter, and boom, fires off the 11.04. Some people just have the dedicated square root key. Like you don't even have to hit shift or whatever. You can just find it. Is anyone having a problem finding the radical button, the square root? Okay. Is everyone getting 11.04 on their calculator? Anyone struggling with it? Don't be afraid, raise your hand. This is the time we got to figure out how to type it in. Because I will expect you to be able to do this for the homework and on my test. So if you don't know how to type it in, you gotta let me know. Especially like if you're coming in on test day and you've been using, let's say you've been using my calculator. I don't know what this is, but let's say you're using mine because mine look like this. So if you're using my calculator and you've been using it for 2 weeks and we have a test, but you forget it, you bring your own from home. On test day, I don't tell you how to use your calculator. You have to know. So if you've been using mine for 2 weeks, on test day, you probably want to use mine because that's the one you know how to do it. Because test day, I don't tell you what buttons to hit. That's not a question I'll answer. You need to know that when you walk in, how to do it. So questions leading up to the test day is when you should be asking those questions. Does that make sense? Okay, I'm going to tell you that right now. You should know how to use a calculator on a test day. I will not tell you how. Okay, but 11.04. Now, what this number is, that's the distance that was on the picture. Because I said earlier, I was holding my fingers on the board and said, oh, this is about 11. I said, okay, 1, 2, because I was holding my fingers about 1 brick apart when I was comparing it on the picture. And I was just using that, counting down, seeing how many I would get to. I said it was about 11, 10 or 11, 12-ish. Yeah, that's the answer. It's exactly 11.04 bricks long. Now, why do you get decimals? It's not perfect. When you go diagonal, the sticks get longer. They get kind of goofy numbers. Here's the best example I can tell you. Okay, let's say you're in shop class, you're in a fabrication class, you're in woods, and they're going to have you do a project where you take a 1-foot board and you connect it to another 1-foot board at a perfect L shape, perfect right angle. When they were in line. You make a perfect L with a 1-foot board, 1-foot board. And the question is, find the board that goes right here. I'm going to tell you right now, the board that you're finding is called an irrational number. It's like your 11.04. It's a crazy decimal that doesn't end and it doesn't repeat. It's the weirdest concept, the weirdest numbers in the world. What I mean by it's so weird, this number doesn't stop, it's always growing. They always find the next digit for the decimal. Now it's a set length. You're seeing it right in front of you. You can see the length of the board. But every single day they have a supercomputer that can find the next number. Because how you find it, it's a square root. You square the one, you square the other one. Because that's how you do it. Square this, add them together, and that equals the other wall. That's what we did over there. This turns to be 1 plus 1, which is the square root of 2. Type in the square root of 2 in your calculator. Like 1.41 something?
4-1.
Yeah. And it just keeps going. That number doesn't end, and it will never repeat. The number is so unique that every single day a supercomputer finds the next digit it'll be. So technically the board is actually growing because every single day they find the next number. Isn't that the weirdest concept? Like the board's getting longer, just a hair longer, because they always find the next number. It's getting more exact, I should say. It's not growing, it's getting more exact. Why these numbers are so unique, an irrational number, it's so long, it's infinite length. There's an actual formula that proves that it doesn't end. Like the decimal keeps going and it doesn't repeat. That means, in theory, all irrational numbers eventually will have your birth date, it'll have your cell phone number, it'll have your address in numerical form, and it has it for everybody and it'll put them in order eventually. Isn't that weird? And it'll have your social security number in there eventually, next to your phone number, next to your date of birth, next to your address. Like, because if it's infinite length, there's infinite possibility that it will be down there eventually at some point down the road. But at no point will it ever start over again and come back to 4-1, blah, 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 blah. It'll never repeat. It's an irrational number. It's the craziest thing in the world. But what I'm telling you is that this number doesn't stop. So there's not an exact length. Now, if you're in Wood's class, what you're going to do is just guesstimate. Well, 1.41 inches long, or feet long. And you'll kind of get close, you'll measure it, you'll cut it, you'll kind of shave off a little bit, but it won't ever be perfect. That's the distance, that's how you find it. It's a diagonal line, it uses radicals. Questions at all about what we're going into? Now, I haven't even answered the question what a radical is. We haven't discussed it yet. Today was the intro to what the formulas are. Okay, all right, last thing today, is we're gonna come back to this tomorrow. We're gonna do a lot more squares. I'll show you how to use your calculators a lot better tomorrow, and how to avoid it if you don't have a calculator. How can you do it? Because yes, at some point you will forget a calculator, and I'll make you do it by hand. Last thing today, we gotta talk about the word midpoint. Let's do that definition. We can hop in here tomorrow. It's the last word today. Last bit of notes. Midpoint definition. Is the location we'll do it tomorrow again. Thought I had another minute to go. Thought I had it perfectly nailed down. Alright, we'll do it tomorrow. Hey, if you brought a calculator, make sure you get them back, please.